Good morning, folks. This is the presentation in Lab 1, which is in week 1, and it's going to be identical posting for both labs in the morning and the afternoon. Now, on the agenda today is these essentially two topics. The two problems that I'm going to do, one of them is chapter 5, which is, I believe, it's an I-beam problem. Deflection of an I-beam under its own weight. And the one in chapter 6 is a C-clamp where we are applying an enforced deformation, enforced displacement. Okay. Now, these things are going to be byproducts of the material that we're going to cover in the first two items. Now, here's my first problem. So we have an I-beam like that, and it's clamped at one end, and then it's allowed to deform under its own weight. So it's going to sag under its own weight. Now, a couple of things here. First of all, this problem is really, it's not a good idea to solve it with solid elements or tetrahedral elements. But we have no choice because at this point, this is our third basically encounter, and we have only covered solid elements, nothing else. However, for demonstration purposes, it's okay. And one of the reasons I'm saying it's not a good idea to do it with solid elements is that in order to get accurate results on the stresses and things like that, you need a fine mesh in a very thin flange that you see here, okay, and the web. And as long as you have a big computing power and you wanted to do that, that's okay. But these elements are not appropriate for the kind of thing that you want to do. Now, if you're asked to solve this thing with as many planes of symmetry as you can find, I hope you realize that the only plane of symmetry here would be YZ. Okay, YZ. Now, if both ends were clamped, and that is not the case here, and this was expected to deform under its own weight, then there will be two planes of symmetry, YZ and XZ. But if one end is clamped, the other end is free, and this is sagging under its own weight, the only plane of symmetry that you have is YZ. So I'm going to do this thing with the plane of symmetry, and then I'm going to remind you how it's going to be done if actually let me start doing it without any planes of symmetry, and then I come back and cut it and tell you what else you have to worry about in the event that you're using that symmetry plane. Okay, so let's go ahead and start this thing. Now these dimensions, I have to go back and forth between them. Let me see for a second. The length is 10 inches, as you can see. 0.25, 1, and 1. Okay, I think I can remember that. So we go here. We start with a part file. There's a part file. And immediately we save it. So File, Save Management, Save As. I'll make on my desktop, I'll make a folder, and I will call it IB. And we say okay. So we're going to save it in there. Okay, so on that vertical plane, I will sketch the cross section of that I-beam. So I'll use a profile, and then I use a few features that you may find useful. You may want to do this in any of these problems. You can do it in a different way, but as long as you get the correct model, it really doesn't matter to us. Okay. First of all, notice that these things are not are not dimensioned properly. So I'm doing half of this basically right now. So dimension, I believe this one is, let me see now. That one is 0.5. 0.5. Okay, don't let it scare you. You can pull this thing out. Wow. Here. Oops. Okay, so this is 0.5. These flanges are all 0.25. So this one is 0.25. 0.25. This is 0.25. 0.25. And let me see now what else we have. The height, the web is 1 inch. 1. Okay, that's pretty much it. Now I need the same thing on the other side. So what I can do, I can select these. Let me see, can I chop it? Well, I guess I'm going to do that. Okay, now I can select these and then mirror it. Let's find the mirror here, mirror it with respect to that line. Okay, good. You have to create this any way you want. It really doesn't matter. But I just also noticed that this web is 0.25, not 0.5. Yeah, 0.25. So let me fix this thing. So this is going to be 0.25. Well, actually, the flange, that's what I meant. The flange is 0.25. 0.25. And this one should be 0.25, not 0.2. 0.25. These are all in inches. Okay, good, good. Exit. And we pad it by 10 inches. 10 inches. The direction doesn't matter. And the other reason I'm saying that, this problem doesn't make sense because look, 10-inch long I-beam with these dimensions, it's not going to sag a whole lot under its own weight. If this was 20 feet, then that would be a different story. But anyway, now I don't like these hidden line here, so let me change the rendering so that I don't see these things. Very good. Now this is made out of steel, so we're going to apply material on it, on that part. And it's steel. You say OK. There we are. And click on the floppy. It's going to save this in that folder. Now, we're going to go to the generative structure analysis. In your case, you're going to get analysis and simulation, generative structure analysis. I have customized my interface so that these are the most commonly used, workbenches that I use. So I put it up here. And in fact, if I click on this, on my arrow here, because I've customized it, it also appears very quickly here. I don't have to go through the menu. But anyway, generative structure analysis, CATIA immediately throws you into the generative structure analysis workbench. Let me change the rendering here to third one. Okay, good, right there. Now, we are doing a static analysis. We say OK. Now, if you want to see your mesh, you say right-click, mesh visualization, and just give it a few seconds or so. There. Now, you can see that actually this is a horrible mesh because in order to get accurate information at the seams here, seam meaning these lines, etc., you need a lot finer mesh. So actually what I'm going to do, I'm going to make this thing from, first of all, I'm going to use parabolic element, number one, more accurate. And for the size, I'm going to use maybe 0.2. Let's see how it looks like. And I have to activate the mesh. Well, that's more respectable, as you'll see. But notice that it takes longer, of course. Now, if you do this thing on your computer at school, it's going to be a lot faster. But actually, I'm going to change those parabolic one into linear because I don't like this delay here. So I'm going to double click on this octree. Instead of parabolic, I use linear. And yeah, just give me a second. You can see this is crying for help. And now when we activate, I think it should come up a lot faster. Yeah, okay, good, good. And this is why on test we ask you to use, unless otherwise stated, we ask you to use linear element with default size, for example. Okay, so deactivate this. Now, one end is clamped, so here is, remember, the process is this. Mesh it, make the model, apply material, mesh it, use restraint to give it displacement, fix displacement, etc. Use the load to tell it what kind of a load it has, whether it's pressure, whether it's force. That's right there. This is the load toolbar, just as a reminder. And then compute. Here's the compute, like the calculator. And finally, the image. Once it finishes, then you use the image to do post-processing. So this is the sequence in general. Now, we clamp this end, that end, or it doesn't really matter. You can clamp the other end if you want. Oh, wait a minute. It looks like I did the face. Yeah, that's what I want. I wanted the face. That's fine. That's fine. If you do the edge, you're not doing what you're asked to do, okay? So, good. Now, the load, I'm not saying how much force you applied here. It's because of its own weight. I'm not saying how much pressure you apply so it deflects. I'm saying it's under its own weight. Now, if you look at this third icon from the left, it says acceleration, and it looks like the planet Earth with a downward arrow, gravity. Gravity is an acceleration, basically. So you click on it, and it says, okay, where do you want to apply acceleration? Acceleration is a body force. It doesn't matter what you pick. It puts it on the whole object. Look, even if I try to pick that corner, it won't do it. If this was a force, I could have put it on that corner, for example, or on a face or on a line. But for body force, for acceleration, it affects the whole thing. And this is the icon for it, but the direction is wrong. So it's not in the direction Y. If this is gravity points downward, so let me change this thing 0. And here, well, if you want, you can put 9.81, no problem. 9.81. Or if you're saying that, wait a minute, I'm not using, well, that's okay. Nothing is going to, this is not wrong. But if you want to say that, oh, I insist on putting it inch per second squared, well, inch per second squared, gravity constant is 386 inch underscore S2. The thing is that it will, because my units, my default units are meter per second squared, as soon as I say kind of, okay, it converts it. It turns it into 9.8, except that put in the wrong spot. You put it here, right there. 386 in the Z, right there. A minus actually 386 inch underscore S2. You see that it immediately converts into meter per second squared, which is roughly 9.8. Good. We say okay, and we run it. Run it means go to this calculator, compute. That's it. Okay. You want to see a deflection? It doesn't take much, imagination to know that this is just going to bend down. There we are. And if you want, you can animate it. Yeah. Good. If you want to know how much a deflection is, number-wise, you click on this icon. You see that? Click on this. This is in the form of arrows. It shows you each point, each node actually, how much in component form moves in any of these directions, X, Y, Z. But if you don't want this kind of a plot, you can either click on the screen, one of these arrows, or remember, every time you generate something, this is added in the tree, or double click on this translational displacement, and you want to, if you select this or that, you have the same effect. And you're going to say average ISO, say OK, and then change the rendering to material shading, and there we are. Anything that you don't like, you can hide. For example, if it's gravity, you don't want to see it, hide it. If the clamp, you don't want to see it, hide it. If this element you don't want to see, just hide it right there. Oops. let me activate this again. Wait a minute. Something, you know what happened? I did something crazy. Because I wanted to hide that thing that was there. Inadvertently, I said delete. So, either I can measure the gain, or let's do an undo right there. Control Z or undo. One more, one more, one more. There. Okay, it came back because inadvertently, instead of saying hide, I said delete. That's why that element was gone. And when I tried to run it, I got that message. Now, anyway, you got the message. You got the message here. Okay, so let me do the following. We're going to repeat this problem using the symmetry. Okay, but before I do that, let me see. Can I show you a couple of things? First of all, uh, let me see for a second. What have we got here? Okay, so let me actually clean this up. Let me deactivate that. Okay, right. For example, let's say that we want to look at translation once again, activated, but not this, under the material shading, average ISO, material shading, which is already there. And I want to cut this. Now notice that there is this analysis tool, and one of the things that we have in it is called cutting plane. So you click on it, and notice that I can cut this. I mean, if you want to see the whole thing, close that, see the whole thing is there. But if you want to cut it and see, for example, the section, what happens inside, you can say just view section only. Right there, you can see that. Okay, and in fact, you can turn this thing around and you can cut it in different directions, etc. So this cutting plane is important if you want to look at inside of something, or you want to make a cut. Excuse me. So we say close. Good. Now I want to go and cut this thing, but how I'm going to cut it, of course, I can scrap this whole thing and go to my model, etc. But the alternative is to go to, you see this, you go to the link part, double click on it, you're going to be thrown into the part design. Right there, you're in part design. And there is this split icon in the surface-based feature. There's this split icon, looks like a saw. You click it, and it says, what do you want to cut it with? I want to cut it with that vertical plane, and it says, which side do you want to keep? So let me keep the other side, although it makes absolutely no difference. There we are. Change the rendering here. So what I've done, I've cut this thing with the middle plane, and because that's a symmetry plane. However, I have to first of all go back to the analysis. So to go back to the analysis, you can either say start, I don't know, analysis and simulation, generative structure analysis, or just double click on any one of these things. It'll take you back. Anyone in the analysis piece. Okay, good. You're back there. This surface that was introduced, I have to put a surface slider on it. Surface slider on that face, because this is a symmetry plane. You can't just leave it alone. Say okay. Now let's run it again. That's the standard message that we get. Now, where is that load, by the way? Load, I hit it. Remember, I hit it, so I want to show you that it's there, and it's in the right spot. We can see that. And if you look at the von Mises stress distribution, you get 41.4, which is very close to what we have with the full model. All right, good. Anything that you don't like, you can hide. If you want to see your elements, let me do that for you. So you go to the you go down here to the question mark, down there, customize view parameters, and because this box was checked, the elements come back. Now, a couple of other things I want to show you. Notice that the colors here are all kind of merging with each other. They're not distinct boundaries. If you want to get distinct boundaries, you see this legend? When you select it, this thing becomes dim. That means you have selected that color. Double click on it, double left click on it, and under this icon, see this three dots, the three dots? Just say not smooth. I don't want anything smooth. So say okay. There, you see that the colors are not merging each other. If you want to move this, you left click select it, you're selecting it, you can middle mouse button down, you drag it. When you're done, left click again, deselect it. If you want to make this thing bigger or the legend bigger or smaller, left click so that this becomes dim. That means you're selecting this legend, and middle mouse button down, zoom in, zoom out, zoom in, zoom out. Good. When you're done, just left click. Okay, so that takes care of our first problem. Okay. By the way, you click on the floppy so that this is fixed. This is saved now, because the previous save that we had was the full model. But if you want to save this, just click on the floppy and it's going to be saved. Unless you want to save both of them, then that's a different story, because you go through file save management and you give it a different name. Okay, you just give it a different name. Okay, that takes care of this. So what's our second problem? Let's get rid of this completely. Let's go to our second problem, which is right here. And I call it a C-clamp with enforced displacement. So what do I mean by that? We have a C-clamp like that. The dimensions are given. The inside face of this hole is clamped. And we take that face, the bottom face, at every point on that bottom face, we pull it down by a 100th of an inch. Okay? Now, obviously, when you pull this thing down, the structure is going to deform. There's going to be stresses developed in it, of course, and we want to predict it. But beyond that, we want to know actually how much force is needed to pull this thing down by a 100th of an inch. That's something that I want to find out, that it's not obvious. Okay? And don't get the impression that, oh, I can plot the stresses and based on that, I can tell you what kind of force I need. Stresses have nothing to do with that force, okay? I mean, they're related to it, but you can't just look at the stress contour and say, oh, the force needed is that many pounds or whatever. We have to do a few things. And I want to do this thing with both with and without planes of symmetry. Plane of symmetry, if there are any. First of all, one thing is for sure, is that there's only one plane of symmetry here, and that is if you cut this into two pieces, left side and right side, the two are going to be identical as far as stress distribution. That, I hope you can see it. That's, to me, it's obvious, but anyway. Now, some of you may be tempted to say, oh, what if we cut it like that? The answer is no, because look, this is not symmetric. Even the shape is not symmetric. There is a hole up there. There's no hole up there. So if hypothetically there was no hole here, and I was taking this top face, moving it up by 0.01, moving this one down by 0.01, then yes, that would be also a plane of symmetry. But that's not the case here. So in this problem, there's only one plane of symmetry. And I'm going to do that first without a plane of symmetry, and then I come back and do it with a plane of symmetry. Okay? All right, good. So there are some dimensions here. We can look at this thing later on. And yeah, let's start with a part file. And say OK. And immediately I save it. So I said File, Save Management, Save As. I'm going to go one level up, create a new folder, and I'm going to call this thing C-clamp. C-clamp. I don't want to mix the stuff in the I-beam and C-clamp. So I-beam is safe there. C-clamp is going to be safe in its own folder. Say okay. All right. Now, on that vertical plane, I will sketch something that looks like a C. I've got to put dimensions there too, but anyway, so something like that. And like, okay, notice that I prematurely let the left mouse button go. So that's why this becomes a line. I don't want a line. I want a arc. So I click on this tangent arc right there. You do it any way you want. Draw something like that. Okay. Actually, I should have done the rest of this. So it's going to be this and that, and there are other ways of doing this thing. I can offset that outside, thingy, outside boundary, offset it, and then those are CAD issues, very important, but those you have done in Dr. Pushka's class. Okay, so first of all, I want to make this thing nice and symmetric with respect to this. I know this top line, control bottom line, control the middle axis. You click on this constraints defined in dialog box, and you make it symmetric. Please, you have to realize that there are many ways of doing things like this. There are other ways of doing it. Top line, control bottom line, control middle axis. Once again, symmetric. There are other ways. Okay. This line, this curve, this arc, control that arc. We want to make them concentric, for example. Concentric. There. Now, there is no tangency icon here, or there's no tangency icon here, but because of the way I've done it, definitely they're tangent. But if you insist, you can always make it tangent. This, control that. We can also make it tangent, but it is already tangent to begin with. There. Good. Now, let's put some dimensions to meet this. So that is 3. The inside radius is 1, and this height is 1. So 3, 1, and 1. So let's go there. This is 3. This is 1. Obviously, because I made things symmetric, this is also 1. And this radius is also 1. And I think that's pretty much all we need. Yes. Yeah. Now there is a hole up there. I can't see. Is this a 3 or a 5? That looks like a 3. Yeah, it looks like a 3. Looks like a 3. Somehow. Yeah, I guess. Now there is a circle there. There is a circle here, which is certain distance halfway between top and the bottom. So 0.5 and 0.5. So let's do that. The radius of this 0.25 first of all. So this radius is 0.25. And if you want to put it exactly halfway between top and the top line, control the bottom line, control the center, click on that, and you say equidistant. So it shifts it a little bit. And then dimension from here to here, 0.5. 0.5. You have to create something like that. How you do it, not relevant. Well, at least to me. Now, we're going to extrude this or pad it by 0.5 in each direction. So mirror extent, 0.5 in each direction. which means it's going to be 1 inch. Okay, let's apply material on this. So apply material. I think I used steel. I said use steel on that part. We say OK. And save it. Click on the floppy to save it there. Our first approach is not to use any planes of symmetry, but I can assure you on the test, I will ask you to all applicable planes of symmetry, so be prepared for that. So we're going to go to Start, and Analysis and Simulation, Generative Structure Analysis. We are doing a static analysis, static default. CATIA sees a solid element, solid object, it immediately meshes it. Immediately meshes. Would you like to see the mesh? No problem. Put the cursor there. Right click, mesh visualization. And there we are. Now, let me deactivate this and ask you a question. Where do you think is the most critical area in this problem? In other words, pretend that if it was to break, that's a bad way of saying it. Things may not break and they may fail. Okay. Where would it fail first? Where would it go plastic first? Where are the places where the biggest stresses take place very quickly? Well, I hope you see that it's in this curved area. This is why I'm saying use finer mesh in critical area, and the critical area is here. These are the type of questions that I may be asking as multiple choice questions. For example, I give you something like that, this problem, and ask you a question. Where is the most critical area in this problem as far as failure is concerned? You have a choice. This face, that face, curved face, or the outside curve face? The answer is going to be the inside curve face. So these are typical questions that you may be expected to know in the multiple choice part of the exam, midterm or the final. Okay, final, of course, doesn't have any finite element stuff in it. Now, how do we do that? How do we get finer mesh here? Now, I showed you in the one of the other videos, so you need to get this let me see now. This toolbar, which has a traffic light in it, this is Model Manager. This is where you do meshing yourself. If you look at the second icon on the left, you click on it. This says Local Mesh size. You click on it, and you select that area. Notice that it did put a default size itself. If you are not happy with this, you can make it smaller, you can make it bigger. But anyway, I'm happy with it. By the way, our element is linear because of what we did in the first problem. You can always change that to parabolic, but right-click Mesh Visualization, and you're going to see roughly that kind of element everywhere except for that inside hole. You can see that. Okay. Now already it shows you that the mesh is really not good here. So actually, you know what I'm going to do? I'm going to deactivate this, deactivate that, and I'm going to go back to this local mesh size, and I also select the inside hole. Say OK. Now look at your mesh. You see small elements here and small elements around the hole. So that kind of patchiness, I mean, faceted faces will go away. Good. Deactivate. All right. Now we know that the inside is clamped, right? Inside is clamped. So you select the clamp and select the inside face. Okay, inside face. Don't select the edges, two edges on the side, because you're not solving the problem that I'm asking you to solve. So that's good. Now, I want to take this edge, this face, and pull it down. Okay, remember, we are not using planes of symmetry here. I'll come back and do that later for you. We want to pull this face down somehow. Every point on it moved by a 1/10 of an inch, a 100th of an inch. Question is, how do we do that? Well, in CATIA, if you want to say, I want to move by that much, first you make it 0, and then you change that. You can change that. And how do you make things zero with a specific direction? So notice that we have the user defined right here, user defined restraint. On that face, in the direction 3 or in the direction Z, 0. That's what this thing means. And we say, okay, now that we put that 0 there, which appears, by the way, in your tree, you can see that right there in the tree. This is the one. This is the one, right? This is the one. You can go to the load and look at the third one from the right. It says N-force displacement. N-force displacement. Actually, remember the name of this was N-force displacement. Okay? So you click on that and it says, okay, what is it that you want to change? Well, it's this guy that I made 0 I want to change. You see some other numbers here. These are from my previous run. So actually, just to convince you that these are not, doesn't matter, here. Just if it's bothering you, I made them all 0. Now it says, what is it that you want to make non-zero? It's this displacement. As soon as I do this, select this, notice that everything gets dimmed out except for that component that you want to push down. And I want to make it minus 0.01. And I say, okay, good. Let's save our analysis. File, save management. Here's my analysis. Save as. In that folder, not this folder, this was in IBeam. Don't mix these up. If this was a test problem and you did this, you said, hey, save. It will take the first problem away, the IBeam problem away. You don't want to put it there. Go to the right folder, and the right folder was called C-clamp, right? Right there. Nothing there. You say, okay. It's so easy to be careless and just overwrite other stuff and say, okay. That's pretty much it. So let's go ahead and run it. There we are. Okay. First, look at the deformation. No numbers. There we are. Animate. This is the way it's supposed to behave, right? This top is clamped inside, and you're taking this face, somehow moving it down by 100th of an inch. Okay. You want to look at deflection? Click on it. Let's change the rendering here. I'll do it from here. Double click. Average ISO. Material shading. There we are. Now, you might say, wait a minute, the maximum displacement is 0.01. That's what I did. Why is it 0.0116? That's because what I enforced is the downward displacement in the Z direction. But this also goes to the left, and it also shrinks sideways. This is the vector square root of downward displacement squared plus x squared, displacement x squared plus displacement y squared. That's why it's a little bit bigger than 0.01. Von Mises stress, it better be biggest here. Right, you can see that. This patchiness, chickenpox look is because you're using a big mesh here, or if you go and use the parabolic one, and I'm not going to use it because this will, my computer will try to die when I use a fine mesh and parabolic, but it's going to be nice and red here without any patchiness. Okay, good. Now, the next question is, well, okay, let me deactivate this. The next question is, how much force is needed to push this thing down? Well, this is something that you have to do, and I'm going to ask you on the test on something like that. You put the cursor there, on the sensors at the bottom of the tree, right click, it says create resultant sensor at the very bottom, on second last one to the bottom, reaction sensor. You click on it. It says, okay, where do you want me to calculate the force? Well, you can always select this clamp, or you can select the stuff that you did to pull this thing down, whatever you feel comfortable with. I'm going to use the user-defined restraint that I used, made it 0, and then changed it right there. And then you say update. There we are. 284, almost 285 pounds. Almost 285 pounds. Just remember this 285 because I'm going to come back and say something about it later on. So remember, you have to put the cursor on the sensor, right click, reaction sensor, uh, you know, second last, yeah. And here, look, don't cancel that. Say okay, because when I mark your papers, then if I see something that you wrote down as the answer on your test paper, I'm going to say, where'd you get it from? The only way for me to know where you got it from is I double click on this for that thing to pop up, and I see that, oh yeah, you have 284 here and you have 284 in your paper. Don't cancel it first time because otherwise it's going to disappear. Now, we want to cut this thing and make a symmetry plane, use a symmetry plane, because you will be asked to do that. Use as many planes as symmetry. How do we do this? First of all, we go back. You have to go back to the part. One way is to go back to the link, extend the link, double click on the part, and you're in part design right there. And get the split right there. Split the saw in surface-based feature toolbar. Click on it. It says, where's your plane that you want to split it by? It's this middle plane. That's why I did a mirror accent, by the way. Which side do you want to keep? It really doesn't matter. Okay. So now we go back to our analysis. You can do it many different ways. You can start start generative structure analysis, or just double click on something that belongs to finite element module. Right there. You're in part design. Your generative structure analysis. Now, we made a cut here. We can't just leave it alone. It's so common for people to forget about putting a surface slider on this. So common. Right there. That's a big loss. If you just cut it, you recognized it correctly. But when it comes to doing it in CATIA, you have to put a surface slider there. Just cutting it is no good. Okay, good. So if you wonder, well, wait a minute, what's all this here? What's all this and what's all that? That's because when we did the problem without planes of symmetry, we put it on that face, so these are still there. But as soon as I run it, this will go inside, okay? It's just inside hole. Or if you go to this restraint here on the clamp, look, I double clicked on it, see? It shoved it inside the hole. Or if you look at this, double click on it, shoves it on that side face. Good. Pretty much it. That's it. So you're taking this edge and moving it down. You have to run it. That stuff doesn't change. Because if you move it down, it doesn't matter you move down half of it, you move down the whole thing. What does matter is the force needed, though. You'll see. Done. Okay, very good. And now, let's look at the von Mises stress if you want. Same thing. These numbers are not going to change. I didn't pay attention to it, but it's not going to change. The question becomes, how much force is needed? Okay, so that's where, let me deactivate that so that you can see that. Remember, the sensor is still there. If I double click on the reaction sensor, and I say that, where is that? That user defined right there. Notice that it's half of what we had before. Remember last time it was 280 something, 85? Now it's half of that. So if you use planes of symmetry and you came up with this number on your paper, how much force is needed to create that deformation, you have to write down 2 times this. 282 in this case, 282, 283, right? Okay. Is that clear? So when you use planes of symmetry in a problem like that, the force is not what this is telling you. The force for the entire deformation, because there are two pieces you have to pull down. You're modeling half of it because of convenience, but the other half is there too. So you have to write double of that. So this is what I'm going to check in your tree. I'm going to check this, and I make sure that on your paper you wrote double of this. Okay. Yeah, so that takes care of the tutorial today, and so in about maybe 10 minutes, or right now actually, it may be posted on in Brightspace. You might have your homework problem posted. Bring it, look it up, please. And you have the GA should be here. And the earliest that you can work on that problem and show it to the GA to get your point is at 10:20. Okay. So basically, we pretend that you need at least 1 hour to work on that homework problem. If you show it to us in 10 minutes, there's something wrong there, in all likelihood. All right, folks, good luck.